This one for all my peeps that pass. God bless they rest. And check it out. Now I'm pound cause it's mad real.
Yo, it's time for Carnegie Mellon University's Future Data Systems Seminar Series. This seminar is made possible by Google.
All right, guys, let's get started. We're excited today to have Jordan Tigani. He's the co-founder and, as his slides say, chief duck herder at Mother Duck. I think professionally, I think legally, you're also the CEO, right?
Possibly.
Yeah. So prior to that, Jordan has worked on many influential systems, including BigQuery and Single Store. Like I said, now he's duck herder. So as always, if you have any questions for Jordan while he's giving his talk, please unmute yourself and feel free to ask a question anytime. If you can't unmute yourself, just post in the chat and I'll try to speak for you. And again, Jordan, thank you for being here. You're in a hotel, which we appreciate you spending time with us and making the effort to talk to us. The floor is yours. Go for it.
Awesome. Thanks so much. I'm really excited to get a chance to talk to this group of people. I've been watching this seminar series for a long time, and very cool to be a part of it. So Andy already gave me the introduction. I do want to show my awesome duckified photo. This is what AI did with my headshot. But yeah, I worked on BigQuery for a long time, and I was a storage tech lead, so I built a lot of the kind of the core storage infrastructure on BigQuery. I got us to about an exabyte worth of data, and then most of it was completely rewritten by people that knew what they were doing. So some of my knowledge is a little bit out of date, but some of this, scales reasonably well. So I'm gonna talk a little bit about some of that database history. But first, I want to make clear some definitions. DuckLake is an open data format, and it includes the catalog that kind of takes what some of the other open data formats for lakehouses are doing, and I think goes beyond it in a more elegant way. DuckDB is not DuckLake. DuckDB is an open source database. Been taking the world by storm, growing like crazy, 35,000 GitHub stars or something. It's not directly related to DuckLake in that you don't have to use DuckDB to use DuckLake, but they were created by the same people. So DuckDB Labs created DuckDB. Hannes, who's on the call, and Mark created DuckDB and DuckLake. And Mother Duck is a venture-backed startup that we run both DuckDB and DuckLake in the cloud. And so I work at Mother Duck. So how did we get here? I want to do just a little bit of history because I think it influences what is so interesting to me about DuckLake and kind of the evolution of some of these lake houses. So the early 2010s and the rise of the cloud data warehouses, BigQuery and Snowflake primarily. And some of the big things we were seeing is we were moving data from sitting on local disks to object stores. Object stores are immutable, so that changed a bunch of things. So much in databases had been used to dealing with spinning disks and disk mutations. Some of that wasn't relevant anymore. For analytics, we were switching from row stores to column stores. So that's changing how data is being laid out. And then, moving from shared nothing, where, basically everything existed in multiple shards to shared disk architecture. And this was really where the separation of storage and compute came about that really allowed massive increases in the overall size of data. And the amount of compute that we were able to throw, and we were able to scale those things independently. So what was important for the cloud data warehouse storage? First of all, file management became a problem because we had all of these immutable data files, and if you kind of leave those alone, performance is going to degrade over time. So we need to compact and coalesce. In BigQuery, had two different things. One was a metadata operation, reducing metadata. The other one was actually reducing small files. And then metadata management, we wanted to make sure we had ACID properties. We were able to have metadata that that lived in a data warehouse, or sorry, lived in a database, and then pointed to the latest objects. And so data objects would be immutable. And then we were able to get snapshot isolation pretty easily. Streaming data was also a problem. Column stores in general aren't great at frequent updates. So essentially what happened was, we built a buffer that buffered in row store, and then periodically would write those out to column store, and then the buffer would also be queryable so that you would get consistent reads. And then as data was getting bigger, reading a lot of data is slow. Even if you can read it, highly in parallel, it's still going to cost you a lot of money. And so kind of the big thing that became really important, kind of probably post 2012, was like, hey, this is really expensive. We need to read less data. And so implementing statistics and partitioning and et cetera, and the ability to read less data. So in a parallel universe, we had sort of the data lake architecture, and people coming from the Hadoop world, we had open data formats, Parquet and ORC, infinitely scalable. You don't have to worry about your schema, et cetera, storing on an object store. But there were a lot of problems. They turned into data swamps. It was hard to govern, hard to know which files you needed. Performance was kind of crap. And then this is sort of the pre-Lakehouse days still. So if you think of like the difference between that and a data warehouse, performance degrading over time, there wasn't really a solution for that. Metadata management, we weren't able to do ACID updates. Streaming and small frequent updates weren't able to do that. Big data, essentially, it will just throw a bunch of leaf nodes at the problem. So the Lakehouse came around to deal with file management, or to solve a lot of these things. File management, was able to do compactions on write or compactions on read. Metadata management was actually able to provide ACID updates. That was sort of the big selling point. Still weren't really able to do small, fresh data. But we're able to help reading large databases or large data sets by providing pruning information so we wouldn't have to read so much data. There were still some problems. Storing data in metadata files meant the file counts exploded. Data freshness was still a problem. Complex transactions that touch more than one table at a time were quite difficult, and some of the more ambitious catalogs are solving some of these problems, but also the read path was very long. So in order to read data, you had to read from a whole bunch of different metadata locations in order to sort of get to the data. And so kind of your latency started out at a pretty high minimum. But I think what we're sort of seeing is a convergent evolution of kind of Lakehouse architectures to cloud data warehouse architectures, with the realization that tables are a better interface to use than files. Obviously, you still have to get to files at some point, but really we should be thinking about tables and working on tables. Databases are a better place to store metadata than object stores. Coalescing in the background can be better than coalescing in the foreground. And then cooperative access control, where kind of every engine has access to all the files, is not a great way of doing things. And so you want to have somewhere to manage all that access. So DuckLake is actually helping solve a bunch of these problems and helping with a convergent evolution by moving the metadata into the catalog. Transactions work because it's using a metadata database which can do transactions. Data freshness works by inlining writes. And the read path link is much better because all you have is a couple of database queries that let you know where the files are, and then you have direct access to the files. So this is from one of the previous Future Data Systems talks that was a couple weeks ago about Iceberg, and how one of the primary thing that the Iceberg planning needed to do was they want to read less data. So how do you read less data I'm going to go through kind of BigQuery, Iceberg, and DuckLake and kind of show what the architecture looks like and how they're similar or different. So the challenge is we're going to take this query. It's a fairly simple query that's on the right, that does a filter between a couple of days. It does an aggregation, um, and takes the top few rows. Um, and so what we're going to really look at is file pruning. So, which is kind of removing the files that aren't actually needed to be read. And one kind of key thing to note is like in file pruning, if you return too many rows or too many files, like you do extra, like you're going to do extra work in the query, but it's not actually bad. But if you return too few files, then you're going to query wrong. So you need things to be basically provably not in the data files. So the way kind of partition elimination in BigQuery works is we basically had a bunch of metadata in Spanner. Spanner is, Google's OLTP scalable data store. We had a tables table and a storage sets table. And a storage sets table had essentially kind of a commit ID. So it's kind of MVCC information because it would also have the ending time as well. And it would also have partition information. And so we could filter out with essentially a SQL query. Spanner didn't quite support SQL at the time, but which storage sets were needed. The storage sets pointed to the files. It was relatively straightforward. Actually, it's a little bit more complicated, and this is one of the really cool things that was added in BigQuery a few years ago, which is there's a separate table in BigQuery. So a BigQuery table that has metadata for the tables. So this is sort of like an Inception style thing. And so the C meta table will have um, the column statistics for the table. And so what you can do is you can actually run a BigQuery query that against that table, and that filters out the data that the files that are actually needed in the query. Um, so what about Iceberg? Now Iceberg, this is sort of the picture of how the Iceberg metadata is chained together. Everything above data layer is metadata, and so in order to do the file pruning in Iceberg, you read the REST catalog. You get the pointer to the metadata file. You read the metadata file, which is a JSON file, and that's going to point to manifest list. Sorry, manifest list is an Avro file, points to manifest files. The manifest files point to sections of data files that are active. You read all those manifest files. Those manifest files have have the filters you need, and then you can basically apply those filters and figure out which files you need. So in the real world, a lot of this stuff is going to be hopefully cached. Of course, when there's an update, then you have to start reading again. And then also the metadata may be really large. And it may be hard to cache. Wouldn't it be nice to put this in a database? So in DuckLake, what does this look like? So these are the DuckLake file and DuckLake column stats are two tables that are used for file pruning, and basically you can run this query. The top is just a CTE, just to make it easier to read. That filters out, by column ID. There's a couple of like hand waves and things that I skipped over here, but essentially, you basically just want to look at in the column stats, where the files have values that overlap with the values that you're looking for in the query. Also that the end snapshot is null. You may also want to, for snapshot isolation, you may want to actually pick a snapshot ID. And so there may be some other details that aren't here. But one of the things is this query looks a hell of a lot like the BigQuery query. If you just sort of squint at it, I'm going to go back a couple slides. Like these two queries are very, very similar. So they're kind of doing the same thing. So what about writes? You have to be able to write. Well, so the key thing you want to do in a write is you need acid properties. So you need it to be atomic. All of the data should show up at the same time. You need it to be consistent. Um, uh, Once it's done, every read after that needs to see it, or every operation after that needs to see the changes. Needs to be isolated. So if you're running lots of these things at once, um, they shouldn't collide with each other. And then durable, once it's committed, it's got to stay committed. So in BigQuery, you basically step one, you create a job, then you run the query, and then the results in BigQuery get written out to Colossus. Um, and then you start a transaction, you create a new storage set to point to those results. You update the table metadata to have some new information, the last updated, the row count, etc. And then you add the new statistics to the C meta table. And then you mark the query job is completed, and then you can commit that transaction. So it's atomic because the whole storage set shows up, or it doesn't show up. If there's a failure, it gets garbage collected. It's being written in Spanner, so Spanner makes sure that all the reads, future reads can be returned. If you run these, the only thing that can collide is the table stats update, and that's easily retriable within that transaction. And it's durable. The data now lives on Spanner, or on Colossus, and the metadata is in Spanner. So in Iceberg, what does this look like? Well, query engine runs the job, stores the Parquet files. Then you write a manifest file, then you write a manifest list, then you write a new metadata file, and then update the catalog to point to the new metadata file. So again, this is atomic. Everything shows up or not, or none. Again, it's consistent. Relying on the object store consistency and the catalog consistency. And isolation is tricky because I think this is where a lot of the Iceberg write difficulty comes in, because if you're doing multiple writes at once, it's even more complicated if you're doing updates, actually. But if you're doing multiple writes at once, you may end up having to redo a bunch of this work. And then of course it's all durable. So DuckLake, on the other hand, DuckLake, you run the data creation task, then create a transaction. So you need to create a snapshot, and then you basically insert in basically some statistics. You update some table stats. You update the column stats, and then you commit the transaction. And so again, the whole snapshot shows up at once, because this is all done in a database transaction. It's all visible as soon as the transaction complete because it's done in a database. It's isolated, and similar to the BigQuery update. The only things that there's only a couple updates here. Everything else is just an insert. But again, those updates can be easily retried. And then of course it's storable because it's a database. So again, this looks very similar to just a normalized version of BigQuery. There's more tables here, but again, it looks quite similar.
So maybe you're gonna jump ahead. Maybe jumping ahead here. Like for MotherDuck's implementation of DuckLake, is it just a DuckDB? Is it Postgres? Is like what's the backing database system for the DuckLake's data?
So it's DuckDB, and I'll get to that. I'll get to that in a few slides. But thank you.
All right, thanks.
Then small writes. So in BigQuery, actually, small writes get written to a special system. Actually, now I think everything gets written to that system, but it's in-memory row store that gets periodically compacted, but can handle very, very high rates of writes. DuckLake, we can buffer the data in DuckLake in the catalog table, in a catalog table. And Iceberg, we still don't have a support for small writes. So just going in for the case for DuckLake, so why do people want a Lakehouse? Um, these are I put quotes around these reasons because this is what people often say, but I feel like these are actually secondary reasons, like the openness of the format, vendor lock-in, um, are things that people are generally willing to throw away if there's a rationale. The cost isn't actually better often, and the performance is actually a lot worse. But I think really what they want is they want to run more than one engine, and often that's Snowflake and Databricks. They also there's a warm and fuzzy that they get about sort of being able to sort of like think that they can touch their data files and kind of understand what's in their data files. And I think the other thing is like there just hasn't been enough description of what you give up if you use some of these lake houses. You do get snapshot isolation, you do get multi-engine portability, you do get near infinite scalability, um, but you do give up a bunch, including a lot of performance. And I think that's something that people don't always recognize. And you also give up the ability to do fine-grained access controls, which if you're giving people access to files, it's very hard to say, hey, we're going to give you, row level access.
What do you attribute that 2 to 10x performance drop of these like Lakehouse systems?
I think partly it's the amount of metadata. I think partly it's also there's usually a tight coupling between the query engine and the data format. In BigQuery, for example, like there were like the same format. The disk format was the same as like the hash table format, so stuff could just be mem copied into memory. Also, like there tends to be sort of like type mapping things that may be slightly different in Parquet, and like so there's kind of a bunch of impedance mismatches if the data format is not designed for the database. My guess is that this will come down to sort of closer to 2x as some of these things get better, and maybe with more advanced column stores, will be even better. Like what was the one you launched recently?
F3, but like that's a sore subject. But yes, there's Vortex, there's F3. Lance is not really compressed really well, but yeah, there's a bunch of these out there now. Fast lanes from Peter.
Yeah. So maybe that will help get closer. And then just one other thought on just constraints. I think often I'd like to keep an eye out for when there's a design constraint that then something changes and that's no longer a design constraint, but sort of like something was built around assuming that there's a brick wall there that you can't pass. And I think one of the brick walls for a lot of these lakehouse formats was they didn't want to store any metadata on anything except cloud storage. Like they had to operate without a separate service or system that was running. And it's not just Hudi, is also like I talked to like one of the Delta architects at Cider a couple of years ago, and he was like, it's like, we have to do this without having an external service. Um, but I think now everybody's adding these catalogs, and I think the DuckDB folks have pointed that out, and it's like if you have the catalog, then okay, we have to run a database, and so you might as well do database things in a database. So databases are great at transactions, logging, inserts, joins, larger data than memory, consistency. Um, you know, they're bad at being easy to be hacked together. Sometimes it's fun. A lot of people do hack them together because it's fun, but you're probably better off using a database than building it. So DuckLake replaces a bunch of other stuff with database. Now here is code that Hannes wrote for that's a minimal Spark connector. It's just to demonstrate that it's not just you don't need DuckDB to do this. And a lot of this is boilerplate, setting up Spark packages. And I won't go too much into this, but basically what it's doing is it queries for what are the files you need, and then it tells Spark to distribute those files to workers, and then this runs the query. So 34 lines, including a bunch of boilerplate is all you need. In MotherDuck, this is what it takes to do something similar. This actually creates a DuckLake table using an external S3 path. It creates a database, then it creates a table. We add a bunch of those files to the tables, and then we can run a query. This particular query is actually from the Dremel paper, and where they, in 3,000 nodes read 85 billion. They did word count on 85 billion nodes in about 2 minutes, and so this is also about 2 minutes, kind of showing that in a scale up system, you can still scale up pretty nicely. And I'm not going to do the demo here, but I did do this demo at Big Data London a couple weeks ago. Okay, so building a hosted cloud DuckLake. Well, so first of all, why do you want to have a managed DuckLake at all? So first of all, like, you may not want to actually run queries from your laptop. For instance, the bandwidth to your laptop is probably a lot worse than the bandwidth to, within the cloud and within a region of the cloud. You may also have, egress fees. The other thing is cloud tools don't know how to talk to your laptop. And so if you're using, Cloud DBT, or if you're using a BI tool that's hosted in the cloud, you need it also to be hosted in the cloud. The other thing is auth. Basically you can have a, centralized, you can let the database choose the auth rather than use S3 for the auth. Using S3 for the auth is super tricky, and then disconnects like what the actual things you care about sharing, which are kind of tables and databases from files. And the other thing is sometimes it's just nice to have somebody else handle the management, making sure it's compacted, making sure it's database or data has been cleaned up that's not being used. You can think of it as S3 tables, the Amazon offering, but for DuckLake. And the other thing is, MotherDuck is a query engine that can be scaled up and down as needed. And so you also have a built-in query engine to do a lot of the work. You can also use other tools, but you can also use MotherDuck as the query engine. Just as a quick background on MotherDuck, MotherDuck has a tenancy model where every single user gets their own scale-up DuckDB instance, and then we can assign those in 100 milliseconds. We generally use hotter storage, so startup can be very fast. And then they shut down when they're not being used, so they scale down to 0 very nicely. The other thing to mention is our client is DuckDB. So if you're running DuckDB on your laptop, you can connect to MotherDuck in the cloud, and then in our web UI, for example, we run DuckDB in WASM in the web UI, and that lets us do things like the instant SQL, where you can get instant feedback, instant query results. So running a managed DuckLake can mean a whole bunch of different things. And this is something we've sort of struggled with, is like who owns the data. So there's the bring your own bucket case where, like, you say, hey, I want you to host my DuckLake database. I want you to host the metadata, but I'm going to own the data. Or you might say, hey, I don't even want to have to bother creating an S3 bucket. Like, I want you to own the S3 bucket. Then there's catalog ownership. Like, somebody might want to run DuckLake catalog on Postgres, but then run the actual query execution on MotherDuck. There's auth. Does MotherDuck do the auth, or is the user going to do the auth? And then who actually does the kind of the maintenance of the data? And almost all of these things are actually valid states. But the thing we're kind of optimizing for is the sort of the fully hosted version. So this is what it essentially looks like. So the client, remember runs DuckDB, talks to a user-facing DuckDB instance, which is the user's DuckLink. So there might be, there are 100 users in your organizations. Each one has their own duckling. Um, and for DuckLake, there's also the DuckLake catalog database, which is itself a duckling. So we sort of have hybrid here in 3 steps, in 3 stages, where we talk to a third duckling, sorry, a second duckling, but a third DuckDB. And the reason that's a separate DuckDB instance is basically so that we can point a bunch of different users at the same DuckLake catalog, and have that all run isolated. And then also that shuts down when it's not being used. So basically, the cost to run a DuckLake catalog is very, very low. Like our smallest instance sizes, we only charge for basically for CPU cycles and shut down, instantaneously. Um, uh, so I just wanted to also mention that sort of like a comparison to if you think back in BigQuery, we had the BigQuery metadata in BigQuery, and here we have DuckDB metadata in DuckDB. You can also use other engines. So for example, let's say you want to run Spark. We're building a Postgres API, which means that Spark will basically think that this is a Postgres DuckDB catalog, and then we will do credential vending. So we can basically, instead of returning the raw DuckLake, the raw S3 paths, we will return signed URLs that give access just to the files that are needed in the query. So we can securely give access to the underlying data to external query engines.
Can you share what the internal protocol is from the user-facing DuckDB, the user's duckling, and then you talk to the DuckDB catalog database? Is that like, I mean, DuckDB is going to send out SQL queries, right? And then are you sending back arrow, or are you just sending back like whatever, like protobufs or what?
So we're sending back, serialized DuckDB um, uh, vectors. So
Okay.
it's not arrow, but it's in DuckDB's internal format. This is part of the sort of the hybrid execution, which we send up serialized query plans, and then we return then results that are
So,
um,
so it's the same as the client. Like if I'm on my laptop, I run the mother duck extension, and when you guys send part of the query out to mother duck, that's basically the same thing you're doing for this, except that they're running they're co-located in the same sort of VPN or whatever.
yes,
Got
exactly.
it. Okay, awesome, cool, thanks.
And it's gRPC, not that it matters that much, but we tried, actually we initially experimented with our flight, but we had a lot of kind of performance and manageability problems, and like it was just easier to use DuckDB's internal native serialization and gRPC.
All right, that's actually an interesting another conversation because the Aeroflight guys are coming to give me a talk in a few weeks as well. So yeah, I'd like to learn more of that, but keep going.
Sure. That was a couple years ago.
Got it. Okay, yeah.
So, fully managed DuckLake, we can do external auth through credential vending. We can do fine-grained access control. And this is still something that we're working on by basically giving partition access. So it's like, you can do row level access control. You can't, like, if you're giving somebody access to files, you can't do pure row level access control. But if you're doing the filter on a partition, then you can guarantee that you'll only have single values or values that match in the partition. And so we can do fine-grained access controls by giving access to partitions. There'll be a Postgres compatible endpoint that makes mother duck make DuckDB look like Postgres. So any Postgres connector can connect to it. And then we also have sort of built-in, very inexpensive, very fast query execution. So finally,
All the auth stuff, like, if I remember correctly, the original DuckLake schema doesn't have any notion of like who can read what. It's just like, right. So that's
yes,
something. So you guys have added extra tables to DuckLake to manage this, and then your platform then enforces that.
yes, MotherDuck adds. So we're not adding tables to it, but it is, we do have user management and data sharing.
Got it. Okay, thanks.
So kind of finally, the Zen is a Zen of data management. The best way to make your queries faster is to read less data, um, especially if there's lots of data around. Uh, Tables are a better interface than files. And if there's things you can use databases for, you should use them instead of re-implementing, pieces of them yourself. That's it. Thank you.
Awesome. I will clap on behalf of the audience. Again, if we have time for questions, so Prakash, I know you want to go for it, so let it rip.
Hey, Jordan, so at some point you talked about small writes being written to or buffered in the metadata catalog database.
Mhm.
So how are they queried? So the mother duck engine can query them, I guess, but I'm sure Spark cannot.
Um, so they're part of the DuckLake specification. And so, a naive implementation would not read those, but a more fully, so a naive implementation wouldn't necessarily do, might not do, you know, pruning based on column statistics. Uh, so a naive implementation might not do, partition pruning, and a naive implementation might not read the buffer. But a more fully featured one would, and it is part of the DuckLake specification. And I think the other way to make it easy is you link in the DuckDB extension, and the DuckDB extension can handle all that stuff for you. And you can even do that in a parallel, in each of your Spark workers, you can link in DuckDB to do that reading.
And do the Spark workers read the data files through the DuckDB extension, or is this a standard format?
Um, they can, but I think Hannes is actually on the call, so he probably knows better. But it's the format is specified as part of the DuckDB spec or the DuckLake spec.
Okay. Thank you.
All right, other questions? Good. I'll use the time. All right, awesome. Is there something that the BigQuery catalog had that you wish DuckLake had? And then for those gaps, are those the things that like MotherDuck is adding to the platform?
I don't think that there's much. I mean, I think actually the DuckLake, I think one of the things is like DuckLake, I think because it's created by database people and it has a lot of the advanced stuff already, like being able to remap columns and like things that I think, are now in the iceberg spec, but I think took a while to get in there and were kind of, relatively difficult. Like I think, those were things that, were built right off the bat.
Yep. Yeah, I 100% agree. Yes. Matt asks, how does DuckLake help the metadata caching issues, or does it? Whether my metadata is in files or an object store or in a database, if my query engine is hammering the metadata, what difference does DuckLake make?
I mean, I think first of all, I mean, databases can do buffer pool management. The data can be, you don't have to read as much of it. I think one of the, because, uh, just like I said, like you can run queries faster if you have to read less data. the same thing applies to metadata. And so if data is um, if the metadata is in a database, you have to read less of the metadata. You have to have less of it in memory. You can keep more of it actually paged out. More frequent things just tend to stay cached versus having to sort of build all that stuff on your own.
Awesome. Jignesh, you want to go for it?
Yeah, I think fascinating talk. I had a couple of questions on the types of workload that you see when people are running MotherDuck and DuckLake. Uh, Obviously, these transactions are presumably very different than traditional OLTP-like transactions that Oracle probably runs and stuff like that. So can you give some flavor, some idea about like the workloads that people are using these transactions for? Is it like append-only workload or dumping streaming data? Or what are the use cases that you're seeing where it is really stressing the transactional limits?
So it's very early, which is one of the reasons I didn't go more into sort of some of the things that we were building. So I think, there are people running DuckLake in production, um, but it's not a hugely widely used yet. And so I do think it's similar to the things that people are doing in other Lakehouse formats. I think it's also, it adds partitioning to DuckDB, and so it helps actually scale the size of data that you can handle in DuckDB because especially if you're doing like time series analysis, you can just look at if you're just looking at the most recent days, weeks of your data. You don't actually have to pull in nearly as much data or metadata. Um, you know, it you know it scales to petabytes versus terabytes or tens of terabytes in a pretty nice way. Um, I think some of the buffer data, this sort of streaming stuff is pretty new, and I don't know whether there's much of that usage yet, but I also think that like it's a great addition to the lake houses, to give you the ability to, you know, actually just sort of fire off a bunch of small writes and not have to worry that you're gonna, explode the metadata.
And I guess a related question is if you're using it with MotherDuck, uh, then how do you scale out? Like, I know you guys do terabytes, but do you guys see a way to scale out to well beyond that, to the types of things you were seeing in BigQuery? Are you starting to see people approaching the scale limits with what you can do with the process model in DuckDB? And, how are you approaching that?
So we're mostly focusing on scaling up. So our largest instance is, 192 cores and a terabyte and a half of RAM, which, is roughly the amount of hardware in a Snowflake 3XL, which is $1 million a year. There's not many workloads that need more than that.
Mhm.
And I think the other thing is our tenancy model means that every single user, every single workload gets their own instance. And so, you can have like one of the reasons you often need a very large instance is because you have a lot of, users hammering it. And um, and so when you have more instances, you don't need the instances to be quite as large. And then finally, I think DuckLake is the last piece in it, which is, if you really, really do need to, restate all 10 years worth of your data, or, run ML training over, 10 years worth of, massive amounts of data, and you need to do it fast, then you can always run Spark. You can always get physical access to the underlying files.
And maybe one last question. Do you guys see the need for integrating with storage in Glacier and things like that? Or like, how far in the S3 layer do you get into in messing around with different storage optimization methods?
So I think what we're mostly interested in is hotter storage. Like, I guess colder storage is also interesting.
Mhm.
That's really, I think, a cost optimization play, but for hotter storage, being able to try to close the gap between, raw DuckDB performance and DuckLake performance. And, like for example, in MotherDuck, when you don't store data in DuckLake, we store it, we have a tiered storage where it'll be, memory, local SSD, remote SSD, object store. And that lets us do really fast startup and can get, really good performance. We're looking into like how do we apply that to DuckLake as well, and being able to cache, use that as a DuckLake cache. Perhaps there are some things in just at least in AWS and the AWS family of offerings, like in S3, like the single zone, that can be helpful with lower latency, or at least for caching. But we haven't gotten too far down that path yet. Again, DuckLake has only been around for a couple of months.
These are great answers, also like perfect technical CEO answers. You like put in just the right zinger in the right places. So nicely done. I have one more question, but I know Yashwant has a hand, so I'll let him go first. And if there's time, I'll ask it.
Let me read Stephen Moy's question. Stephen Moy asks, WD is a catalog. So he basically wants to know what is the specific methodology that MotherDuck is using to allow multiplayer or multi-user mode for the DuckDB catalog.
It's essentially a routing problem. And so, so DuckDB, right now only supports single, if you have a database open for write, it only supports, it takes an exclusive lock on the data. And so you would only be able to run one of those processes at once. And so effectively what we're doing is we're having the catalog database, and we would route all of the requests to the catalog. But basically all the catalog requests should be relatively small and lightweight. The only exceptions would be the inline data, and I think we may have to do something special for the inline data.
Got it. All right, Yash, your turn.
Thanks. If I understand correctly, what you're saying is that all the metadata for DuckLake is stored in a standard SQL table or a standard SQL table, and that's the openness of it. Are customers wary of this? Because if the service provider is providing the SQL execution model for the metadata as well, are they wary of like transitioning from one to another compared to an open table format where they have all their data in their own object store?
I have not heard any concerns about that being in SQL tables, especially because there are multiple, like you can use your own Postgres instance. You can use your own, the standard, or the DuckLake standard, was defined to be implementable in virtually any databases. It needs sort of very few specialized fancy database things. So it is quite open, and I haven't heard any concerns with that.
Okay. I guess the part I was trying to get more about is like, if I'm running a DuckLake warehouse, and let's say it's not provided by MotherDuck, by maybe Databricks or Snowflake or someone, who owns the metadata in that sense? Is that running as part of like a Snowflake table or a Databricks equivalent table or someone, or like do I, as a customer running my DuckLake data, have my own SQL table I'm running my metadata in?
So who owns if it's not running in MotherDuck, anybody can own it. So any Postgres, like you could have your own Postgres that you're hosting yourself, and as long as that Postgres is accessible from the Spark job or from whatever you're running it from, you'll have access. So like, okay, yes, it might be somebody else. It might be an Amazon RDS instance, but like, I don't know, do you not trust Amazon RDS to be open enough? Like if you're super paranoid and want to run, every line of code based on open source that you own, then yeah, you can run your own Postgres server.
Makes sense. Got it.
But I guess like a situation I was curious about. It's like if you have Snowflake, you have Databricks, you want them to interoperate, you want them to talk to each other. So that's why you would use like the Iceberg offerings, right? They write all these manifest files, they write these Parquet files, and they can read each other's data. They can both commit, and well, maybe not both commit, but they can at least both read, right? So in a situation where, let's say DuckLake was part of the Iceberg spec, and they were both speaking DuckLake, how would that work? Would it be I guess it's expected that the user would host it separately, or
Well, so I don't know about DuckLake being part of the Iceberg spec, but I'm not exactly sure how that worked. But let's say Snowflake implemented a DuckLake connector and Spark implemented a DuckLake connector, which I think, should be in the works, and we're starting to work on a Spark connector, just because we believe that that's something that should exist. Even if it doesn't work, use MotherDuck, we believe that we all win when if DuckLake becomes ubiquitous and becomes usable from any engine. All it takes is implementing an open source connector and all of these things, and then they can all share the same data and metadata. They just need access to whatever the DuckLake catalog endpoint is.
I see.
I would add,
Thank you.
I would add that Ben and Yash are sitting at Snowflake right now, so they can go implement it. They can do it.
Of course.
That would be a great idea.
Yeah. All right. Superhits ask, what access control model is implemented in DuckLake, and does its fine-grained design allow embedding or enforcing access control primitives within individual files?
So DuckLake does not have any access control as part of the spec, but MotherDuck has added access control. It's relatively basic. It's just ACLs, and the and it's actually quite coarse-grained right now. It's ACLs on databases. I was describing a partition level access control. That is something that we are working on. We hope to launch that in the next couple of months.
Got it. So my next question is, are you guys running a separate analyze path to fill in all the column statistics? Or are you assuming that whoever is telling DuckLake, here's the files I have, we'll fill that in for you?
I think it depends. And this also gets a little bit beyond my knowledge of DuckLake. But if you are writing the data out and you can collect that data as you're writing it, then you can run you can run the DuckLake update queries on your own to provide those. The DuckDB extension, the DuckDB DuckLake extension, has a set of functions that you can call that will go and generate whatever metadata is necessary from the underlying files.
So to be clear, but as MotherDuck, I'm asking whether you guys do that.
Oh.
Like
we will do that we use the DuckDB DuckLake extension, and so yeah, we will add those if people don't provide them themselves.
Got it. Okay.
And as we're writing them, yes, we do add those things. So yes.
Got it. And then is there anything proprietary is not the right word, but anything that's custom to MotherDuck you guys are storing in extra stats that like the regular DuckDB DuckLake extension doesn't do?
No, I mean there's a bunch of stuff that we had to do in hybrid execution to sort of to make it work nicely, but nothing that's like specific that's going to make it run faster or better.
Got it. Okay. All right. Any last questions for the audience? All right. So my last question would be, if you had a magic wand and you could solve any engineering problem at MotherDuck or DuckDB, but if you want to make about MotherDuck, that's fine. What would that be? And you maybe think of it like, what's a 1-year magic wand fix, and then what's like a 5-year thing you wish you guys could tackle right away?
Wow, that's a good question. Uh, I don't know. I feel like we just have a bunch of DuckLake roadmap work items that are all queued up, and like I would love if those could just sort of magic, all the stuff that I've described be magically shipped completely. But it's going to take a little while.